Hello students, and welcome back to the Quarantine Lectures. Dr. Heinz with you here. Today in episode 2.5, what we're going to be talking about is deformation and fracture of materials. Hello students, and welcome back. So for today's lecture, we're actually going to be using our old friend silly putty. But first I want to go in and just recap a couple terms that are relatively important to what we're talking about today. So deformation and fracture. We know from what we talked about last time, our stress strain curves, that when a load is applied to a material, it will first cause the material to change shape, right? If that is low enough, if that force is low enough, let's go look at our curve. If that force is low enough, it stays in the elastic region, it'll deform, but it will return to shape. If it's large enough, it'll deform, and it will not return back to its original shape. And of course, if that load then gets higher and higher and higher, if it's high enough, it can actually cause the material to break. And then fracture, remember, is separation of the material into two or more, in the case of a shatter, pieces under the application of said force. So most of these mechanical properties will describe a material's tendency to or not to deform or fracture. So first, let's talk about brittle fracture. So remember when we were looking at our silly putty, that if we pulled it fast enough, we could get it to break into two very clean pieces, right? So looking at the fracture line here, right, you can see it's pretty straight. So that's really what we're looking at here. This is what's known as brittle fracture. If little or no plastic deformation occurs before fracture, material is said to have experienced brittle fracture. Such fracture occurs in the elastic region of the stress strain curve, below or near the yield point, right? So a material like this that would fracture and be sharp might not even have the actual curve part of the curve, if you want to call it that. It might just look like a straight line with an X at the top. Okay, brittle fracture occurs suddenly and results in complete separation of the material. In practical terms, this is the snap. Okay, this break is typically perpendicular to the applied tensile stress, right? So what we're showing here, right, this is the way that this is actually the way we pulled it. Fundamentally, if it were in our tensile test, it was like this, right? The break occurs perpendicular to the applied force, which was in this direction. Okay, so again, that picture there shows very clearly what I'm trying to show with the silly putty, which is you get these flat lines of fracture. All right, so the next phenomenon we want to talk about is something called necking, right? So what you're seeing here in this slide is our original kind of this is a three-dimensional tensile test sample. But what you're going to see is as it pulls, you're going to see it get very thin in that region. And that's kind of what we expect, right? As it gets thinner and thinner and thinner, that's when you start to arc over that curve in the stress strain curve, right? So if we do this properly, right, we pull this, you're seeing how it's actually getting thinner in that middle area, right? It's stretching and it's getting thinner, right? We're not just stretching the material. The material is continually getting thinner and thinner in the middle, and eventually it will get so thin that it will just break, right? This phenomenon is known as necking, okay? It's a localized reduction in cross-sectional area of the sample as the material elongates. Ductile fracture. In ductile fracture, significant plastic deformation will occur before the material fractures, right? So this would be materials with a very arcing curve, right? Necking can occur, as we've shown here, in three different ways, right? If something's super brittle, it'll just pop and it'll just break, right? And that's what we see in A. In B, we see something that is completely highly ductile, and this is called rupture, where it just continually pulls apart until there's just nothing left and it just gives you those perfect little points where it used to be attached. Or you can get, in the case of C, something in between where it's more of a ductile fracture. It doesn't go completely to rupture, but it still has a ductile fracture where it did shape a little bit, right? You did observe necking before it broke. So if we go to Course Handbook page 59 for our sample problem, samples of 3 different materials are subjected to tension until they break. Rank the samples below from highest ductility to lowest ductility. All right, so let's go through the samples one by one before we show the answer. So sample A we see was a rectangle, and as we pulled it apart, it just snapped. Sample B exhibits high amount of rupture. We see that it continued to stay together. It was highly ductile, and then finally it just fell apart. And sample C was pulling apart, it was deforming some, and then it eventually just broke. So if we were to rank these samples from highest ductility to lowest ductility, sample B obviously shows the most ductility because we saw it go all the way to rupture, followed by sample C, who deformed some before it broke, and then last, the least ductile, will be A because it just snapped on us. That is consistent with what we're showing. All right, so now if we look at just this plot, which I'm showing over the screen right now, this is ductile fracture kind of put into perspective on our stress strain curves. In the elastic region, you see that our material is fine, right? It's our sample stayed the same. It's gotten a little longer, but it goes back to where it was. In the first portion of the plastic region, you see that we start to get stretching. Once we get past the maximum stress, we actually start to observe the necking, right? That's when you start to see that localized reduction in cross-sectional area. And that, of course, is why that curve starts going down, is because as it gets thinner and thinner and thinner, you don't need the same load to extend it anymore. And eventually you get to ductile fracture there on the X, where you see that you had some sort of necking before breaking. On the flip side, if we were to look at the stress strain curve of brittle fracture, the elastic region is relatively same with what we've consistent with in that section. Section of the curve, it goes back to where it was. We then go into the plastic region where we see it start to stretch, but then we ultimately hit brittle fracture. There's no necking present because it hasn't had a chance to kind of get over that curve. We just see it snap. So it goes elastic to plastic to a direct snap, and that's what we see in more of a brittle fracture type behavior. So again, we can use these stress strain curves to make the decisions that we need as engineers, right? Do we want our material to stretch first? Do we want it to just snap, right? What do we need for our application? How can we use it? And that's how we can look at those stress strain curves to make those decisions. All right, so this kind of concludes our material properties. What we're going to come back with next in the next lectures, we're going to start actually looking at atomic properties of materials and how that relates to their behaviors.